Welcome to the Explainer. Today, we're going to unlock the secrets behind, well, pretty much every secure thing you do online. From sending a private message to buying a coffee, there's this invisible lock at work, and we are going to see exactly how it functions.
So let's just dive right in with the fundamental question. This is a problem that has stumped spies and generals for centuries. If you have a secret message, you need a secret key. Simple enough. But how do you get that secret key to the right person without an eavesdropper just grabbing a copy first? Solving this one problem is the key to all modern digital security.
To really get why this is such a tough nut to crack, let's take a look at the old school way of keeping secrets. It's a method that works perfectly, right up until it hits one critical, deal-breaking snag. So this old way is called symmetric cryptography. Just imagine Alice and Bob have a super secure safe. They both have an identical copy of the key. Alice can pop a message inside, lock it up, and Bob can use his copy of the key to open it. It's fast, it's efficient. For protecting what's inside, it's actually fantastic. But here is the massive dilemma. What if Alice and Bob are on opposite sides of the world? How does she get him his copy of the key? If she sends it over an open channel like the internet, some snooper, an eavesdropper, can just copy it, and now the bad guy has a key to their secure safe. This is what's known as the key distribution problem, and it is a huge, huge hurdle. So, how did we solve this? Well, the breakthrough came back in 1976 from this revolutionary paper by three guys, Diffie, Hellman, and Merkle. And their idea was just brilliantly simple, inspired by an object we see literally every day. They just imagined a mailbox. Think about it. Anybody can walk up and drop a letter through the slot, but only one person, the owner, has the physical key to open that box and actually read the mail. This concept, which they called asymmetric cryptography, is all about splitting one key into two completely different but mathematically linked parts. And this is the absolute game changer. You get a public key, which is like that open mailbox slot. You can shout this key from the rooftops, post it on your website, give it to absolutely everyone. Anyone in the world can use it to lock or encrypt a message just for you. But, and this is the magic part, the only thing that can unlock that message is your private key, the one that you keep totally secret. Now, what's amazing is that just a year after this concept was proposed, it was turned into a real practical working algorithm. This thing, named after its inventors, Rivest, Shamir, and Adelman, became the most widely used public key system in history, RSA. Look at this timeline. It just shows how fast this idea took hold. It went from a theoretical paper in '76 to a world-changing algorithm in '77. So let's pull back the curtain and see how RSA actually forges these magical linked key pairs using some really clever number theory. It all boils down to this 6-step mathematical recipe. It starts simply enough. You just pick two massive secret prime numbers. Then you multiply them together to get a number n, which becomes part of your public key. Now, the real magic happens in the next few steps, which use a super clever branch of math called modular arithmetic to create two linked numbers, E, which is your public key, and D, your secret private key. It's this beautiful math that creates that unbreakable link between them. Okay, this looks like a bunch of numbers, but this is where it all clicks. Let's see it in action with really tiny numbers. So Bob picks the primes 3 and 11. He follows the recipe and gets his public key, which is 33 and 3, and his private key, which is 7. Now Alice wants to send him the secret message 4. She uses his public key to do a calculation, 4 to the power of 3 modulo 33, which gives her the scrambled message 31. She can send 31 over the open internet. Only Bob, with his secret private key 7, can do the reverse calculation, 31 to the power of 7 modulo 33, to get the original message back, 4. It looks like math, but it really works like magic. Okay, so you might be thinking, if this is so brilliant, why don't we just use RSA for everything, right? Why do we still even need that old-fashioned symmetric cryptography at all? The answer, in one word, is speed. The really complex math that makes this asymmetric crypto so secure also makes it incredibly slow. We are talking up to 1,000 times slower than the symmetric stuff. Trying to encrypt a huge movie file with RSA would literally take forever. So in the real world, your computer does something really clever. It uses a hybrid system. When you connect to a secure website, you use that slow public key method for one tiny crucial job, to securely agree on a brand new temporary symmetric key. As soon as you both have that shared secret, you switch over to the super-fast symmetric method to encrypt all the actual data.
And that's what makes the whole system so unbelievably elegant. You are truly getting the best of both worlds. You get the fortress-like security of asymmetric crypto for that critical key exchange, and you combine it with the blazing speed of symmetric crypto for the rest of the conversation. It's a perfect partnership.
So what's stopping an attacker from just breaking the math? What really makes this whole system secure? Well, this brings us to what's basically an ongoing security arms race.
You see, the entire security of public key crypto rests on something called a one-way function. The best analogy is mixing paint. It's incredibly easy to mix blue paint and yellow paint to get green, but it is practically impossible to take that bucket of green paint and perfectly unmix it back into pure blue and pure yellow. For RSA, that one-way function is called integer factorization. And this is where the security really lies. An attacker can see your public number n. That's public. They know it's just your two secret primes multiplied together. But to break the encryption, they have to figure out what those two original primes were. And for a number that is hundreds of digits long, that is an impossibly hard math problem for even the most powerful supercomputers on Earth. And this table right here, this shows you that arms race in action. As our computers get more and more powerful, the numbers they can factor get bigger. So to stay ahead of the bad guys, we have to make our keys longer. A few years ago, a 1024-bit key was considered pretty solid. Today, for any kind of long-term security, we need keys that are 3072 bits or even longer.
And this leaves us with a final, pretty provocative thought. Our entire digital world, all of it, is secured by a math problem that is only hard for the kinds of computers we have right now. So what happens when a totally new kind of computer comes along, like a quantum computer, that can solve this problem easily? Well, the race is already on to find the next generation of invisible locks.